Hey, good morning, class, and welcome to 4.2.2. Hopefully, the first three lessons have gone well for you, and watching the videos has helped. Please remember that your teacher does have office hours available, and right now, those office hours, only a handful of students at most happen to be attending them. Please use those to your advantage. Um, and you can get your questions answered. You can talk about essential skills. Uh, all of those topics can come up, and you can fill in the misunderstandings that you have. Today, the goal is to be able to graph rational functions with point discontinuities and slant asymptotes. We're going to go through problems 64 through 67 today, and then there'll be a second video covering questions 69 to 72. Who is the greatest of them all? The overall goal of this portion of the lesson is twofold. One is to determine end behavior of a polynomial. And in the process of doing that, we also need to figure out what term of the polynomial has the greatest effect on the output value as x gets very, very large. And so we're going to take a look at this polynomial p sub 1 of x right here. And as x happens to get larger and larger, if x is 1 or 100 or 100,000 or a million, which term has the greatest impact on the overall value of p sub 1 of x? So let's take 1 and plug it in for x. Well, 1 squared is 1. 4 times 1 is 4. And a negative 12 is still just a negative 12. Now let's plug in 100. 100 squared is 10,000. And 100 times 4 is 400. And the constant negative 12. And if we add all those together, we have 10,388. Now if I take 100,000 and I square that, I'm going to get a huge number. And 100,000 times 4 is 400,000. Constant's a negative 12. Now if I add all that up, I'm going to get a huge number. If I take 1 million and I square it, I'm going to get a gigantic number. And 1 million times 4 is going to give me 4 million. My constant's negative 12. If I add up all of those, I get a gigantic number. So as x goes to positive infinity, p sub 1 of x is also going to positive infinity. In other words, as x becomes very, very large, p sub 1 is becoming gigantic. But what happens as x goes to negative infinity? P sub 1 of x, does that go to a negative infinity or does it go to a positive infinity? Well, let's check this out. X is a negative 1. Negative 1 squared is a positive 1. 4 times a negative 1. Negative 12. All that adds up to negative 15. Now if I take a negative 100 and I square that, I get 10,000. And 4 times a negative 100 is a negative 400. Constant's a negative 12. And if I add all those up, I get 9,000 588. Now if I take a negative 100,000 and I square that, I get a huge positive number. And a negative 100,000 times 4, well, that's a negative 400,000. And then the constant of a negative 12. Add all those up, and it's still a positive number. That is huge. And a negative 1 million, if I square that, I end up with a gigantic positive number. And 4 times a negative 1 million is a negative 4 million. The constant's a negative 12, and you add all those up, and you get a very gigantic, monstrous positive number. So this is still going to end up going to a positive infinity. What I'd like you to do is pause this, and then either by graphing or building a table, determine the end behavior for p sub 2 of x. So in other words, as x goes to positive infinity, where is p sub 2 of x going towards? And as x goes to negative infinity, where is p sub 2 of x going towards? Pause it and come back and check your work. Okay, hopefully you took some time to graph it or build a table. What I did is I built a table by plugging values for x into the equation. As you can see, as x gets very large in a positive sense, as it goes to positive infinity, p sub 2 of x is also going to a positive infinity. It's becoming a very huge positive number. And as x becomes very small in a negative sense, or a very large negative number, p sub 2 of x is becoming a huge negative number. Sometimes we can refer to this as it's becoming very small also. So this is going to a negative infinity. Now, we will take a look at what happens to polynomials that are divided. And for each function below, substitute large positive and large negative values in for x, and then decide what happens as x goes to positive infinity, and also as x goes to negative infinity. So if I take this first one, I want to take a look and really think about what's playing a role. So I built a table for this first equation, r sub 1 of x, and here is what's happening to my y value as x is getting larger. I didn't even choose very large numbers. I went from 0 up to 20, and you can see that these values keep getting smaller and smaller and smaller. In fact, they keep getting closer and closer to 0. And if I look at the graph, my graph is coming up, and it appears to get to cross the x-axis, and then it keeps coming back closer and closer to 0. Over here, I chose x to become more negative, so larger negative values. And what's happening again to y? It keeps getting closer and closer and closer to 0. Now again, this is hard to see unless you're to zoom in. This graph actually crosses the x-axis, and then it comes back towards the x-axis. So it's still becoming closer and closer to 0. What I would like you to do, before we go any further, one way to come up with the end behavior for a function without having to make a graph is to examine the most influential terms. So if I want to figure out what's happening to y as x goes to positive infinity or as x goes to negative infinity, all I have to do is take the most influential term in the numerator and most influential term in the denominator and examine that. So if I examine r sub 1 of x, and I only look at x squared over x cubed, well, as x gets large, my denominator is going to grow faster than my numerator. Therefore, as x goes to positive infinity, r sub 1 of x has to go to 0 because the denominator keeps getting larger and larger. And then the same would be true as x goes to negative infinity. My denominator is going to become larger in a negative sense relative to the numerator. So r sub 1 of x is again going to go to 0. So you really only need to analyze the most influential term. Now what I'd like you to do is pause this and determine the end behavior for B, C, and D. And I'm going to erase all of this stuff, so if you want to take a photo of it to keep it, please do so. When you come back, it won't be here. Okay, welcome back. Now if you take a look at part B, I'm just going to examine the most influential term in the numerator and denominator. So r sub 2 of x equals x squared over x cubed. Well, as x gets very, very large, my denominator becomes much bigger than the numerator, which results in a much smaller number. Now you can see that if you actually take the time to reduce this fraction. X squared over x cubed will reduce to 1 over x. And what happens as x gets larger and larger? Well, this becomes a overall smaller and smaller number. It approaches 0. And what happens as x becomes a larger negative value? Well, this is going to become a value that gets closer and closer to 0. And what about part C? What about the end behavior here? Now, the end behavior ends up going to a negative 3. Now, let's analyze that by taking a look at the graph. Now, before we do so, I have to erase some of this so that I have a little bit larger screen to work with. And here is a photo of C. And I'm going to erase just a little bit more up here. You can see that if I was to draw in a horizontal asymptote at 3, that this graph, as x becomes very large in a positive sense, in other words, as x is going to positive infinity, this graph keeps getting closer and closer to a negative 3. And as x goes to negative infinity, this graph keeps getting closer and closer to a negative 3. Therefore, the end behavior as x goes to a positive infinity or to a negative infinity is a negative 3. You can get that value by actually analyzing r sub 3 of x equaling 3x squared over negative x squared. Reduce this fraction, and if you reduce this fraction, you get a negative 3. So by analyzing the most influential term in the numerator and the most influential term in the denominator, you can help determine end behavior of these rational expressions. Here are 3 more for you to do. If you'd like to pause this and then come back to check your answers, please do so. I would emphasize doing at least 2 of them. Do D and E, and if you have time, do F as a little bonus. All right, welcome back. In R sub 4 of x, or part D, if I take the most influential term in the numerator and most influential term in the denominator and analyze that fraction, it reduces to x. And so as x goes to a positive infinity, y is going to go to the same thing, positive infinity. It's going to where x is going. And as x goes to a negative infinity, then this output of the most influential terms is also going to be a negative infinity. In part E, if I take the most influential term in the numerator and denominator, say that's going to determine my end behavior, well, then I end up with 5x cubed over x cubed. The x cubes cancel, and the end behavior will be 5, regardless of whether x is going to positive or negative infinity. And in part F, if I take the most influential term in the numerator and denominator, I have x cubed over a negative x squared. That reduces to a negative x. So as x goes to positive infinity, this output then is the opposite of a positive infinity or negative infinity. And as x goes to negative infinity, this is then going to be the opposite of a negative infinity, which is positive infinity. Again, please verify this by making graphs. All right, on this page, we're going to graph rational functions, and I've already taken the liberty to do that for you. So let's take a look at f of x equaling x squared plus 5x plus 6 all over x plus 1. If you take time, go to your calculator and type it in, use a standard viewing window, and you're going to get a graph that looks something similar to this. And you notice we've got these 2 parts, kind of what we call hyperbolic in shape. And it looks like we end up having a vertical asymptote over here on the left of the y-axis. That looks like that's at about an x equaling a negative 1. And there's actually going to be this thing we will address a little bit later called an oblique asymptote. But more about that later. We want to take and say, well, if we have a vertical asymptote at x equaling a negative 1, and I'm looking at my function, that's because my denominator would be 0 if x is negative 1. That's what creates that vertical asymptote. The oblique asymptote comes from another process which we may get to yet today. Let's look at the second equation, g of x. This looks almost the same as f of x, but yet the graph is so much different. And the reason being is when we write both of these in factored form, f of x in factored form, g of x in factored form, notice how I cannot reduce anything in f of x. These factors do not reduce. But in g of x, I can reduce the x plus 2. And that just leaves me with x plus 3. That's a linear equation. Therefore, the graph of g of x, because of the reducing of 2 factors, g of x becomes a linear relationship. But there is some discontinuity. Notice when x is a negative 2, there is no y value. So right in here, there's actually a hole in your graph. It's nothing that you can see on most calculators, even if you try zooming in, but it does exist because those factors reduce. So if you were to graph this by hand, what we would want you to do is draw in the graph that you'd see on your calculator, put a little circle there, and then you can continue with your line. Okay, so on this page we're going to try to match equations with certain discontinuities. We have three equations on the left, h of x, f of x, and g of x, and then we're looking for three different types of discontinuities and kind of why do they exist, or two different discontinuities and why do they exist. One, which equation has a hole? Secondly, which one has asymptotes, and which one has neither? So if you want to pause this and try to match that and come up with an explanation why, then you can come back and check your answers or just follow along if you'd like. Welcome back, and I'm going to start with the bottom one. The reason why I'm starting with the bottom one is I know that I have two factors in the denominator, a factor in the numerator. Nothing's going to cancel, and so my denominator equals 0 when x is a negative 3 and when x is a negative 4. Therefore, this is going to match with asymptotes at x equaling a negative 3 and x equaling a negative 4 because no factors canceled or reduced. Now in the second one, if I write this in factored form, I have x plus 2 times x minus 2 over x plus 2. What I see right away is I have a pair of factors that reduce. Therefore, this has a hole at x equaling a negative 2. And by default, this one has to be neither. This is in factored form. I cannot factor it any further. And if you actually graph this, I believe you're going to get something that's got a little bit of a bell shape to it. And it has neither vertical asymptotes or a hole. Well, class, hopefully you had a good time watching another video. There's going to be plenty more of this as we go through the term. Please, again, consult your teachers with their office hours. And I look forward to talking to you next week. And I wish all of you the best of luck on your essential skills test tomorrow. Please take some time to prepare.